getting into this vibrational spectroscopy. I love this stuff. It's what I do in my research. I do principally FTIR. But of course, FTIR, Fourier transform, infrared spectroscopy is all about molecular vibrations. So let's get into it and review a little bit of what we talked before. So recall, we applied this potential energy operator from our Hooke's law, right, where we basically called our vibration two masses on a spring, right? And the potential energy of those two masses on a spring can be described as 1/2 times kF times x squared. Here now, x is our displacement scale, okay? And so that displacement is how much does the bond move relative to its equilibrium bond distance, right? So these vibrations, it doesn't compress the two masses to where they're touching, right? These vibrations look, something like this, right? Where they're not quite compressing all the way. They can't because there'd be too much nuclear repulsion, all right? So displacement is really meaning kind of like the relative motion of mass 1 and mass 2, all right? And hopefully you recall that as we have a larger force constant, right? So we remember that Kf equals the force constant. Okay, so the larger our force constant is, the stronger is the bond, and the less displacement there is. Okay, and so we can see that with increasing Kf, the parabola, our potential energy curve gets narrower and narrower. Okay. So this is about as much as we did, and obviously we solved the Schrodinger equations and got quite a complicated set of equations from that, right? We had to use the Hermite polynomials, if you remember. And so the solution to the Schrodinger equation, okay, so solution to Schrodinger was this, where each energy is quantum number nu plus 1/2 times the quantity h bar omega, where omega is the frequency of this vibration, okay? And we recognize that nu is the quantum number. It can be 0, 1, or 2, right? So this is the solution in terms of joules. So we'll put that in parentheses right here, joules. But if we wanted the solution in terms of wave number, so here we use the little tilde, right, g. And so you notice it's still got the same nu plus 1/2, nu plus 1/2. But now this quantity h bar omega has been replaced by this nu tilde. Okay? And this nu tilde, that gives us the wave number frequency of vibration. So this is the value on our spectra. So for example, if we were looking at a carbonyl stretch occurring around 2100 wave number, that 2100 wave number comes from this equation. And recall the 1 over 2 pi c, and really it's a factor of 1 over 2, or excuse me, 1 over h c. That's how we convert things to wave numbers from joules, right? So you notice that it still has this same base equation, right? Square root of kf divided by the effective mass. Okay, so we can still see that there. So this factor in front just converts the joule solutions to a wave number solution. And of course, we'd have to convert all of our meters into centimeters, so we can make that 1 over centimeters. Okay? So now, for a totally idealized, what we would call a rigid rotor, this is what we would see. Okay? But a real molecule will have what we call this Morse potential. All right? Because a real molecule, in a real molecule, the bond can break, right? In this, this perfect parabolic motion, our rigid rotor, as we get to high quantum numbers, right? And I'll notate the quantum numbers here on our, our perfect simple harmonic oscillator model, or our rigid rotor model, right? We could keep going up and up and up and up quantum levels, quantum vibrational levels, and there'd be no bond breaking. We know in reality there is some bond breaking. And so that's where we use this real molecule solution, which we call the Morse potential. Okay? And we're going to look at that here, momentarily. Okay? So let's just talk a brief review of the selection rules. A molecule must contain a permanent dipole moment. Okay? Or it must vibrate in a way that gives it a dipole moment. So CO2 right here is this really good example where we know that technically CO2 doesn't have a permanent dipole moment, right? It's symmetrical. However, as long as it vibrates in some type of way that gives it a dipole moment, it will be IR active. And that's what this picture is showing you, right? Here we have IR radiation propagating. And we recall that, that light is an oscillating electromagnetic field. All right, so this is the oscillating electromagnet of light. And you notice here that a molecule with a dipole moment, or one that can vibrate in a way that gives it a dipole moment, will be stimulated by this oscillating electromagnetic frequency. And in fact, it is the frequency of this IR light that is stimulating these bonds to vibrate more than what they'd be vibrating at their ground level, right? So at the ground state, at the nu equals 0 state, which we expect, right, 99% of the molecules, we expect 99% of the molecules to live at this nu is equal to 0 state, okay? When light with the correct frequency, and this would be an infrared frequency, is irradiated on a molecule, that can influence it to be displaced even more. So in other words, it sends it to a higher vibrational energy level. Okay? And we also remember, right, our selection rule, one level at a time. Delta nu can only be plus or minus 1. All right? And so now if we think about those solutions to our Schrodinger equation, right, and here we're looking at the wave number solution, if we go to calculate delta G of nu, right, where we recognize that's what this is going to be, right, the difference between these two levels is going to be given by this delta G equation. Well, we know that it's going to be nu plus 1 minus nu. It could also be nu minus 1, right, because plus minus 1 at a time. Well, if we do the algebra here, this factor of 1/2 is going to go away, and all we're left with is just simply nu, okay? So in other words, right, that the delta, the difference of that, just gives us the vibrational energy, okay, given by nu tilde. I know nu is used a bunch of times, so keep that straight, right? So this one is the, I'll say, quantum number. This one is the actual energy, of course, expressed as a wave number, right? Okay, moving along. So now let's get into this Morse potential here, okay? So the equations that govern molecular vibrations are only approximate, right? That's that rigid rotor model, okay? Or sometimes also called the simple harmonic oscillator model. So the simple harmonic oscillator parabolic motion does not allow for bond dissociation at large displacement, as I showed in the previous slide. So molecular vibrations are what we call anharmonic. So this simple harmonic oscillator model, right, is this perfect parabola. So it's symmetrical. That's what makes it harmonic, okay? Real molecular vibrations are anharmonic. In other words, they can be broken. They are not symmetrical when we go to higher quantum numbers. And we can see that given here by the Morse potential. Okay? And so here is the equation that governs the Morse potential. And what's important to note here is that dE gives us the depth of the well. So this quantity right here gives us the full depth of the well. All right. And then to actually get the D0, the bond energy, a little bit of algebraic manipulation is done. So we'll say that's DE, and we'll say this one's D0. A little bit of algebraic manipulation is done to go up that level, nu equals 0. And that's also based on a few things we know, like the equilibrium bond length and its effective mass. Okay? And so what this also means is generally we always see the fundamental transition in spectroscopy, right? From 0 to 1. Okay? However, in some cases, we might actually be able to skip a level. And so go up 2 levels at a time. And that is due to this anharmonicity. Okay? So that, depending on the strength of the vibration and the width of the well, so as you might imagine, as the well gets wider, right, if you recall this description of the particle in the box model, as the well gets wider, those energy levels are going to get closer together. And so a very, what I'll call a floppy bond, so a not rigid bond, right, can occasionally violate that fundamental transition from 0 to 1. Okay? And so now here you can see I got a whole bunch of equations on here, and I'm not going to spend a whole lot of time discussing these because you're going to dive right into these on your Spec 2 assignment. And so I'll just briefly comment that here you can see up to this point, this is our normal solution to the Schrodinger equation, which assumes harmonic motion. Okay, so this assumes SHO, simple harmonic oscillator. And now we've got this other part on here that describes the anharmonicity. Anharmonicity, yes. So that extra term is given as this extra quantity here with this factor XE. And XE is a ratio of the vibrational energy to the depth of the well. Okay? And so typically what is done in spectroscopy is these quantities are calculated via data fitting. So via curve fitting. We record the spectra and we get those values from fitting the data. And I'm going to describe to you how we do that. In a moment, I'll describe how we do that. We have to first, of course, start thinking about when we would expect to see this anharmonicity. We talked about it with floppy bonds, okay? But also, we can see it when the molecular rotations are coupled with the molecular vibrations, okay? And so that's given as rho vibrational spectroscopy. In other words, gas phase FTIR, okay? So let's get into that. And this is one of my favorite things to describe because there's some really good classic physics going on here. And I like to think of this phenomenon as the quantized ice skater. So we'll call this here the quantized ice skater or quantized figure skater, however you want to think of it. Okay. So let's go back to the basics. All right. So we recall that our Morse potential, right, this potential energy curve, that really represents the entire ground electronic state, right? And so you did this on your exam, right? You calculated the energy of the one sigma level, right? This would be that electronic energy level, okay? So we recognize that here is the ground state, nu equals 0, where we expect most molecules to be. Here is nu equals 1 and 2 and 3. And within this ground electronic state and ground vibrational state, there are J levels. Okay, so there are rotational J levels. And so here you can see as a much better zoom in of that, where at the nu is equal to 1 state, I will have a population of rotations, right? Especially if this is a sample at room temperature. Also within, and so we call that J double prime. So the J double prime right here, those are the J levels for the ground state. So then now in the vibrational excited state, there are also a population of J states, and that's given as J single prime. Okay. Let me find my place here. Okay, so what's happening with this quantized ice skater is kind of like what we described with bond distortion when I was talking about microwave spectroscopy. So if you imagine a fully elongated bond, right, it's stretched out to here, and it's rotating, all right, it's going to be rotating at some given, frequency based on the molecule's rotational constant and, of course, temperature. But now, as that bond vibrates and comes in, the molecule is going to rotate faster. As it stretches, it's going to rotate slower. As it comes in, it's going to vibrate faster. And so this process is going to be very dynamic, right? It's going to slow and then increase, and then slow and then increase. I could do this all day long until I get too dizzy, which I think just happened. So what happens now is this molecule elongating and compressing can stimulate the rotational levels. Okay, and so that's what you can see with these arrows right here, right? Where we might have, a molecule going from the ground vibrational state in the ground rotational state, right? That would be this point right here. And as it goes through some excitation, the vibration actually excites at a J level. Okay, so you can see now it doesn't go directly to the nu equals 1. It goes to certainly to the nu equals 1, but it goes to the J equals 1 within the nu equals 1, right? And so you can see now from these other arrows that all kinds of other possibilities exist. So let's organize all of those possibilities. Okay, and so they are organized into what's called the P branch, the Q branch, and the R branch. And I want to really keep in mind, I want to stress that this is gas phase. Okay, we don't observe this phenomenon in liquids or solids because as you try to rotate a liquid or solid, there's another molecule in the way, right? There might be another molecule that it's hydrogen bonded to, right, that's preventing it from rotating. Or certainly in a solid lattice, you can imagine how that will prevent a molecule from being able to rotate. So we only see these types of transitions in FTIR with gas phase molecules. Okay, so let's be very clear about that. This is for gases. So as you can see now, here we've got a whole bunch more levels indicated. So here we've got the ground vibrational state. Okay. And then here we've got the excited vibrational state. And you can see, for one, the first one that I'll point out, okay, the Q branch. So this is showing multiple lines to the Q branch, which is not correct. That's a bad figure. There will only be one line for the Q branch. Okay? And so the Q branch is when it truly goes from nu equals 0 and j equals 0 to nu equals 1 and j equals 1. Okay? So we'll start by noting that in the Q branch, we have a nu plus 1. So I'm going to write I know the way I'm writing that looks kind of goofy, but that's kind of standard spectroscopy notation. Nu goes to nu plus 1. and delta J equals 0. All right? And so we're going to call this set, this transition, I'm going to call that new tilde sub q, and I'm going to say that equals delta S, which is a function of quantum number nu and a function of quantum number j. And I'm going to talk more about what this delta S function is momentarily. Okay? So now, what about the p branch? Okay, well here we've got the p branch over here, and let's just find one to make an example out of. So if we look at this very first line right here, so it's in the nu equals 0 and the j equals 1, and it goes up to the nu equals 1 and the j equals 0. All right, so you can see here for the p branch, delta j is -1. And of course, we recall we can only move one j value at a time, right? So we're not going to have a delta j equals 2 or anything like that. And of course, we're still talking about the fundamental transition here, okay? And so now we're going to come up with an equation on the next slide, this delta S equation, okay? And we shall see that we'll start with the same form here, but the way this is going to go, so that's delta S, so any one individual S is going to come from nu plus 1 and j minus 1. Okay? And over here with the q branch, we'll note that that's nu plus 1 and just j. You'll see what I'm going to do with these equations on the next slide. And now if you look at the r branch, where you can kind of guess where this is going, here if we start at nu is equal to 0 and j is equal to 0, this goes up to the nu equals 1 and j equals 1. Okay? So for our r branch, we still have, right, the fundamental transition, but now our delta j is plus 1. We're going to come up with an equation to describe those transitions in the same way. Okay, so the delta S is going to give us the actual energy of that vibration, right? Remember, the difference in energy levels is what we observe in spectroscopy. And now this S function is going to be nu plus 1 and j plus 1. Okay? So let's do some algebra with this thing. And if you want to follow with me, go for it. Okay? So the P branch, right? We recall, we said that was this delta S as a function of nu plus 1 and j minus 1. And so now when I go to write this equation down, okay, this is the delta, right? Final minus initial. So that's going to be S of nu plus 1 and j minus 1. So this is my final. And now my initial is just going to be nu and just j. All right, so that's my initial. Okay? And so how do we get all of these? Well, we remember that the vibrations follow this. Let's just do the simple equation, right? Our vibrations follow this delta G equation, okay? And our rotations, let's see if I can go all the way back to the rotations. Where'd we go here? Yes, okay. And our rotations follow this, this F equation, right? J times J plus 1 times B. Okay, so that's what we're going to do. So let's put all of that together. All right, so first I'm going to start with the initial, because that's likely easiest to see right away. And so this whole initial state is going to be given as nu plus 1/2 times nu tilde. So we know that, and if I were, of course, to put in nu is equal to 0, right, then I would have it. And now that's going to be plus j times j plus 1 times b tilde. And so when we do these other two, the Q branch and the R branch, all of our initial states are going to look like this, where I just have to supply the the correct quantum number, right? And that would be J is equal to 0 and nu is equal to 0, okay? But something magic happens when we take the time to do the algebra. So let's code in the, let's write down the final state, okay? And so now that's going to be nu plus 1 1/2, right? So we're doing this generically. So I've substituted nu for nu plus 1, okay? And that's still times the vibrational energy level nu. And then now this is going to be plus, and this is going to get a little hairy, so hopefully I've left myself enough room. So I'm going to replace this J with a J minus 1, okay? And then I'm going to replace this J with a J minus 1, and that's a J minus 1 plus 1. And now that's all times B tilde, right, the rotational constant. And there's my final state, okay? And so now I'm not going to do all of this algebra, but if I were to do this algebra, right, distribute all these things through and treat this generically, and I'm going to treat it generically by not putting in a value for nu. We could, if we wanted to. We could put in 0 for this nu, and it would all work out, right? If I put in 0 right here, then 0 plus 1 is 1, and we haven't done anything illegal, okay? But if we were to keep all of this through and do the algebra on this, we would come up with the following equation. It would be equal to nu tilde, remember that's the energy level, or the actual, the actual energy that would show up on the spectrum, the vibrational constant, minus 2 times J times B tilde. And that's what we would get. It would be this simple little equation right here. Okay, so I'm going to write that down again so I can keep it all boxed off. So nu plus, or nu P, the P branch, right, is nu tilde minus 2J times B. And so what's pretty cool with this, it doesn't matter what the vibrational quantum number is because we're only ever dealing with the fundamental transition, right? But now when we start talking about the J levels, you can see what's going to happen as we go up in J levels, right? If J were equal to 0, then that whole thing goes out and the vibrational energy is just equal to the vibrational constant, right? But what if J is equal to 1? Okay, well, if J is equal to 1, that's going to go nu minus 2 times B prime. Okay, well, what if nu is equal to 2? Well, then that's going to go nu minus 4 times B prime. Well, what if nu is equal to 3? That's going to go nu minus 6 times B prime, or B tilde, sorry. And there's something really cool going on here. So I'm going to back up really quick and go to back to our microwave rotational spectroscopy. And recall here that we said these rotational lines will be spaced every 2 times B. Right? Not quite. Obviously, we also remember there's some centripetal distortion, right? But in general, they're spaced every 2 times B. And so what's really cool, what we just did, this was the kind of the little magic that I was talking about. Here we can see now each of these rotational lines will be spaced every 2 times B, which is super cool. Okay, so if we were to repeat this process for the Q branch, where now my nu sub Q, right, we know is equal to this delta S function, which is just going to be nu plus 1 and J, okay, which is just going to be equal to, let's see here, nu plus 1 and J for my final state. And my initial state is just going to be nu and J. So if we were to put all of that together, then simply all that it equals is just nu. So one line for the Q branch. And in fact, if our gas, so remember, this is only for gases, right? Our Q branch is where the liquid form of this gas would show up in the IR spectrum, right? Because you can see there's no J dependencies, all right? So if we were looking at like HCl, okay, and I'm going to show you the IR spectrum of HCl next, As a liquid, there'd only be one vibration, the hydrogen-chlorine vibration, right? And it would show up at this value. But if it were a gas, however, we're going to see these rotational lines. And I'm going to cut straight to the chase here. And if we were to do the same thing for the R branch, I'm not going to write any of this down, right? You could work it out for yourself if you like. But if we do all of this for the R branch, then we get that this equals 2 times the rotational constant times J plus 1. Okay? And so once again, if we were to go through a series of J values, right, if J is equal to 0, then this is equal to 2 times B. So I did, what did I do? I did something wrong. Oh, this is, excuse me, 2 times B times J plus 1, sorry, plus nu prime, right? So if we were to go through these levels, right, for J is equal to 0, that's going to be 2B plus the vibrational wave number. So I'm going to put tildes on there so we know that those aren't quantum numbers. If I were to look at the J equals 1 state, right, that's going to be 4B plus nu. If I were to look at the J equals 2 state, 6B, etc. So we're going to see spacings every 2 times B. Okay? So I've got some glorious FTIR gas phase spectra. These were all generated in Chem 363 from various PChem students. So here they are, Marcos, Micah, and Will. So 2015 was a great year for the Schlenk line. It was just working spectacularly. Those of you in lab will know what I'm talking about. In 2021, the Schlenk line has not been working spectacularly. So let's talk about what we see. So first example, HCl. Okay, and we'll just back up here for a second and keep in mind, oops, where'd we go? I lost track. So P, Q, and R. Okay, so the Q branch appears right in the middle. The P branch is J minus 1, and the R branch is J plus 1. And so you can see with the way that this goes, with the frequency of absorption, if I have my, with the way that this is graphed, okay, this is going, so it's going to be, let me just make sure, yes, it is going to be opposite of what it looks like in this picture, right? Because remember, in spectroscopy, we always kind of plot it backwards, right? We plot it with high energy first because that's a small wave number, a small wavelength rather, I should say. So that means technically this is R, this is P, and this is Q. And we notice that the Q branch is missing, and that's because our HCl is a gas. It can't vibrate without stimulating a rotation. And so you notice for all of these other gases, HBr, DCl, carbon monoxide, right? Hopefully you can see that there is a missing Q branch because none of these gases can vibrate without stimulating a rotation. Okay? And so if we just keep pointing out some features here, so these are definitely spaced every 2 times B, but there's some really cool actual real molecular effects going on here that we talked about with that and harmonicity, and that's exactly what you're going to do in your Spec 2 assignment. You're going to digest data like this in a worksheet that gives you direction that's going to help you explore those and harmonicity effects. There's also another feature that I want to point out here, and you notice in the HCl, I'll circle this one for example, it's a doublet. So I'll zoom in on that. And so if I were to zoom in on that peak, we would see one big one right here and one little one right here. And hopefully you can tell each one of these J transitions has that doublet. So what is going on with the doublet there? Well, remember, HCl, and specifically chlorine, is made up of chlorine 37 and chlorine 35. So the larger peak corresponds to H35Cl because the chlorine 35 is more abundant than chlorine 37. And so that little peak is H37Cl. Okay? And so we can see those isotopes in each and every one of those J transitions because in our random sample of HCl, it's going to have some H35Cl and some H37Cl. Both have similar cross sections. So both appear in the same region of the spectrum, right? However, we can see that because of the difference, because of the effective mass of the two, it does make those rotational and vibrational constants just slightly different. And what's really cool, here's the DCl spectra. The isotope effect is really prevalent in DCl. And that's due to the mass difference between a D35 chlorine and a D37 chlorine. And what's going on with this thing here is in the HCl situation, the mass difference between a hydrogen and a chlorine, be it a chlorine 35 or chlorine 37, is significant. That is a significant difference in mass. So it just looks like as if HCl is attached to some stationary wall and only the hydrogen is moving. DCl, however, because the deuterium is twice the mass of the hydrogen, the reduced mass between these two does not work out this way. And in fact, the deuterium pulls the chlorine along with it. So the deuterium is actually massive enough that it can pull that chlorine. Okay? And so you can see it makes a huge difference in the actual energy levels here. So you notice our Q branch for HCl would be around, maybe 2870 or something like that. Okay? But now notice that our DCl Q branch is actually around 2100. So what this means is because this DCl is also pulling the chlorine and the chlorine pulls back on the DCl, it has the effect of looking like a stiffer spring constant, all right, which is pretty cool. And so here you can see HBr, and HBr behaves pretty similarly as chlorine. We don't really see the isotope effect at all in HBr. There are bromine isotopes, right? There's H79Br and H81Br. However, the situation that I just described with HCl is even more present in HBr. So the reduced mass between an H79Br and an H81Br is insignificant. So you don't really see a separation of those isotopes like you do in these two scenarios. Okay? And of course, here's our carbon monoxide. And the most noteworthy thing of pointing out here is the B values. So here you can see that remember, the spacing between each one of those peaks is 2 times B. Let me point that out on something I can easily notate, right? The difference between each one of these is 2B. Of course, the difference between these are going to be 4B. But now what you can see, or hopefully you can see this, the rotational constant for carbon monoxide is much smaller than the rotational constant for HCl. And that's due to the length of the bond. Okay? So all this is really cool stuff. I'm going to end it there because I've been talking quite a while. I hope the students in 363 can make some beautiful looking rotational spectra. Actually, these are row vibrational spectra. So there's both the confluence of rotations and vibrations going on in these spectra. And these are really pretty to look at, really fun to analyze. And this is, like I said, what you're going to be getting into in Spec 2. Okay. I'm going to end it there, folks. Have a good one.